Okay, good morning, everyone. Welcome to the last exercise day in the course. We are here. We are at the final topic. I hope you all had a, fun journey. You learned something, hopefully. So, without further ado, let me go through today's presentation, and then we can talk a bit about exercises and about the next two project days. So, share screen. We are recording. Cool. Okay, so the last topic is scaling applications. And what I mean by this is when you have something that works, now it's maybe time to optimize it. So there is this famous quote by Donald Knuth, which is like a quite famous computer scientist, that you should forget about small efficiency, say about 97% of the time. Premature optimization is the root of all evil. Premature optimization is the fallacy of the engineer to say, I really like to sit down and make this code faster. And that's not really what drives value in the end for business. What drives value is you create a product that can give some value, and then you figure out, hey, it's not, my users are complaining about latency. I need to make it faster. Now I go in and optimize it. So this is the reason why this is like the very last topic, because you basically need a working pipeline before you should begin on this. So a distributed application in general, because that's how we scale things today, is computing on multiple threads, devices, nodes in parallel. That's like the core concept. And what we can run in parallel in general, it can be our data loading when we do training or when we do inference. It can be the training algorithm in itself. And of course, we can also run the inference algorithm in itself in parallel. So I have some notes about the training part and the inference part. And then for the exercise, you can look at the data loading. So the key takeaway in this small presentation is that doing things in parallel is not free. There is a trade-off. So when you run things in parallel, of course, you can compute twice as much and so on. But these two devices now needs to talk to each other. So saying, hey, number two, I'm doing element 1, 2, 3, 4. Okay, I'm doing 5, 6, 7, 8. Cool. When you are done, you also need to kind of aggregate it together. This is a cost, and then we need to balance that with how well we are utilizing our devices. So if we are only doing like simple addition, like sending one element to each device, saying, hey, could you add 2 to this? That's really bad utilization of our devices compared to the high communication cost of actually sending data to them. So let's look at training. To understand training, we first need to go back to the very first lecture where we talked about devices. I hope you remember, in general, we can say there are 3 devices. We have the CPU, the oldest of the ones. It's like this general compute unit. You all have one in your computer, hopefully. Else I don't know what it runs on. In general, you can say it can run between 2 and 128 parallel operations if your program actually can take advantage of it. And CPUs were intended to do unit operations. So one number with another number, multiplication, addition, and so on. These very simple add-sum operations. Then along came the GPUs for computer, graphics processing units. So it's meant for rendering really visual things, but today we are also using them for training deep neural networks. And in general, we are in now the 1,000 to 10,000 parallel operations we can do. And the thing we figured out with GPUs is they are really good at doing operations on vectors. So this vector, let me get my pointer. So this vector with this vector, multiplication and probably addition. And then we can do matrix multiplication very, very efficiently. Then along came Google and said, this is not enough. Let's create a specialized unit. And they come up with the TPU, the tensor processing unit. And this is like a specialized AI unit in general. And we are now in like the 100,000 parallel operations that can be done. And it's simply because now, instead of doing things on 1D tensors, we can begin to do things on 2D tensors, which is much more efficient. So, regardless of what device you're running on, like you can essentially run things in parallel, but the more specialized it becomes, the more things you can run in parallel. The second factor we kind of always need to consider also is device memory. So device memory is just how much data, how large a model can I store in memory. And there's like these standard numbers. So for a CPU, that's your RAM. Usually it's around, that should be 32 to 64 on like a high-end desktop. In your laptop, that's more like 16. A GPU, consumer standard GPU, has around 12 gigabytes of VRAM, we often call it. And a TPU is usually around the 64 on the low-end units. But for CPU, you can, I think most motherboards today support around 2 terabytes of RAM. The largest GPUs we have only have around 80 gigabytes, unless you have like some of the super hardware from NVIDIA, which nobody can get their hands on. And TPUs, we can be in the 32 terabytes of like in-house memory for doing computations. And this figure over here, it's kind of an old one, but essentially they talk about what happens when you move from CPU to GPU to TPU in terms of training this exception network. And as you can see, it goes down. So think about what device you're running on and how much memory you have available. This has been increasingly more and more true as we encountered these large language models, which has like, we cannot even fit them on one GPU today. When we talk about distributed computations, there's also many levels to this. So at the very top level, the simplest thing you can do is to do data loading in parallel or in a distributed sense. So meaning like I have a data set consisting of many image files. Now I ask my CPU saying, spin up 10 workers. Worker 1 gets the first image, worker 2 gets the second image, and so on. So now I parallelize that I can get more information in, which I can feed to my GPU, which is the actual unit I care about having a high unit utilization. Then I can parallelize my model. So that means running on not just one GPU, I can run it on 2 GPUs, or 8, or 256, if I can figure that out. And then, of course, I think maybe the most simple one, even though it's at the bottom here, it's experiments. Like if you have done one DB exercise in doing sweeps, you have this agent you can spin up, which can do an experiment for you, but you can spin up another agent, and you can thereby run things in parallel. You can also do it more simple. You open a terminal, run your experiment, you open up another terminal, type in, run another experiment. You're doing things in parallel. Hooray! So, okay. The way we do distributed things is with these very simple, basic distributed operations. And there is 6 of them. The first one is called scatter. Okay, so some terminology. In general, we say that there is always one device that's the main node or the master node, and that's usually rank 0, so the first one. And then we have everything else, that's the worker nodes that are doing some of the computations. So in a scatter operation, we store our data on rank 1 or rank 0, and we send like indices to each of the workers. Or we take whatever workload we have, we split it by how many workers we have, and they receive it. Gather is the opposite operation. Now we've done some computation on each device, and we send it back to the main worker. Reduce is similar to gather, but there is some atomic operation added on top. So in this case, we not only send the elements to the main worker, we also add them together. Then you have all reduce, where it's like everyone sends everything to everyone, and then add it all together. So this is when you really want to make sure that all your workers are doing kind of the same thing. So we have an example later, but think gradient in neural networks. If we have a copy of a model on every device, we really want to keep the gradients in sync. So we are updating it in the same way on all devices. And that is what all reduce is for. This is, of course, also one of the most expensive operations to do. We have broadcast, that's sending the same thing to all workers. And then we have all gather, that's all reduce without the reduce operation. So the first way we can do training in a parallel sense, or the first way we came up with it, is the most stupid one, and that's why we came up with it. So let's assume you have your model, you have your batch of data, you have, in this case, you have 4 elements. And what you do is you say, hey, let's start out by sending each element to each of my worker GPUs. I also send my model out. Then on each device in parallel, I say, I take my, GPU1 takes my elements, send them through. GPU takes their elements and send them through, and so on. And at the end, we gather everything together. And then when we want to do the backward pass, it is only done on the worker GPU or the first GPU. We calculate gradients, we scatter them out, we do the backward pass in parallel, and then we reduce in the end. So this works, and it's a one-liner in PyTorch, but I hope we can all agree that this is kind of inefficient. Can anyone see why? We have to send the model every time we want to do a single update. We have to send the full model from the worker GPU to all other GPUs. So some smart people, not me, realized this is stupid, and they came up with distributed data parallel. So this was called data parallel because we are processing data, the forward step and the backward step in parallel. Distributed data parallel, the only key change here is now we also store a copy of the model on each device. And the other improvement here is saying, instead of at batch level, we split up our data. We from the beginning at data loader level, saying batch 1 will go to this device, batch 2 will go to this device. We do what is called a page locked host memory, which is saying like now I've already pre-allocated which batches should go where. So this whole data loading also becomes more efficient. But as you can see, we start out with having a copy of the model on each device. And now we just load in these sub-mini batches, which has already been locked in some predetermined order. We calculate the laws or the gradients. We need to, of course, now we are not sending the model, so now we need to do this all reduce of the gradients, and we also do the backward pass in parallel. So I hope this is one very expensive operation, but compared to, let's say we have 1 operation, we have 2 operations. This is parallel, 3 operations, 4 operations, and 5 operations. So in the first one, we have 5 distributed communication operations. Here we only have 1. Big improvement. Then came along very large models, which is a problem in here because there is the core assumption that we can actually store the model on every single GPU. So what to do now? People came up with something called fully sharded data parallel. This is a bit complex figure, but essentially what happens is you are not only, what happens is you have your first GPU here, you do your forward pass here, and then the end, let me start over. You have a large model that consists of maybe 2 layers, two very large blocks. You can store block 1 on one GPU, and you can store block 2 on another GPU. So you process your data through GPU 1, and then you take the output of block 1 and send to GPU 2, and that process. So you basically split your model over multiple GPUs. This ensures higher communication cost and so on and so forth, but there's simply no way around it when our models become so big that they cannot fit in one GPU. So we need to essentially do this fully sharded when our models are too big, and it costs some communication cost, but there's no way around it. Yes, so the name referred to, we take the model and we shard it, so we split it over multiple GPUs, but these processes can still run in parallel as with the last one. Okay, so just simple summary. Data parallel, very simple to use. It's a one-liner. It's really, really slow because we are replicating the model and just destroying it at the end of every single step. Distributed data parallel, I think it's the fastest one if you can fit your model in one GPU. But it also has a high memory requirement because we are actually storing a copy of the model. And then you have fully sharded, use it if you have very large models. So in PyTorch, as I said, data parallel, you just use this wrapper around your model. Very simple. If you want to do DDP, you need to set some master address and master port on where things should go when you start communicating. You need to initialize a process group. You also need to do this page hosting of memory. You need to spawn multiple processes, and I think I forgot like 5 other steps. It's freaking hard to do by yourself. And then you have model parallelism, and just don't do it by yourself. Of course, you all work with Lightning at this point, so I'm just gonna recommend not necessarily Lightning, but just use some freaking framework that has implemented this for you, because it really can take weeks to set up yourself. And in Lightning, you can set the number of devices you want to run on which accelerator. It can also, I think accelerator is equal to auto by true automatically, which means it just picks whatever is the best device it can find. And if you want to, so modern, when we talk TPU and modern motherboards, a motherboard usually can only support 8 GPUs. So that means if I want to run on more than 8 GPUs, I need to run not just on one compute node, I need to run on multiple nodes. So that's essentially what we're saying here. We want to run on each node, we want to run on 8 GPUs, and we want to run on 32 of these compute nodes, which in the end means that we are doing 256 GPUs training. This is very nice, but there's also, so there's a thing I don't cover here, but whenever we do an operation on our device, on CPU, GPU, RAM, and so on, there is some data that needs to be sent somewhere. So we need to send data from the CPU to the GPU or between GPUs. We need to send between RAM, CPU, and so on. When we begin to move like compute unit to compute unit, that network that goes between them is really slow, like really slow compared to what is on the actual motherboard. So it's when we move between nodes, it can be really slow. So this is where we really have to think about, is the communication cost really worth it? Yeah, and I just wanted to say, of course, we all know today, scale is the matter of the game in deep learning. The more scale you have, usually the more performance you have. And there is also, so there is a framework from Microsoft called DeepSpeed. It is kind of state of the art for doing very efficient training, and you can include it in your own training, but you can also, like we have a strategy argument. And then the other thing we have seen today is this precision. So support for half precision or 8-bit precision or quantized integer precision. Yeah, you can go really, really low today. Another trick in PyTorch, and I also think I mentioned this in the beginning, is just remember to compile your model. So from PyTorch 2.0, they have this very simple line of code, model equals torch.compile your model. And what this does internally, so we talked before about when you build your model, you essentially build a computational graph. And what this compile does is what we call operator fusion. So it goes in, looks at this and saying, hey, I actually have another operation that does all this. And then it merges into one simple operation. So when we begin to communicate also between operations, instead of having to send it through at least 1, 2, 3, 4, 5, now we can send it through one compute unit. And just think of these small errors, that is a communication cost. So the less errors we can have in our computational graph, the better, because the less communication we have to do. And there, if you go online and search for Torch compile, you can find graphs like these, essentially saying, so this is the Llama 2 model, that's one of the big LLMs, that if we take and turn on compile, this is other, this SDPA method is also another compilation method, we can get like huge performance increases. Just at the last minute here, I also just quickly wanted to touch about inference, because that's what I talked with a lot of people yesterday, not about monitoring, but about your projects. And it seems you are stuck in the fast API at the moment. So maybe you are wondering, hey, how can I speed that up? And the best way to speed up inference in a production setting is to do batch inference. So we have a simple app here. It takes in an item, it maybe cleans it, it does prediction, we format the predictions, and we turn the output to the user. Instead, we could have like a batch predict input, which now takes a list of items. And then we do like, we process this into a single batch, and then we send the whole batch through. And that's because all I talked about parallelism and so on, this is faster. Of course, now you need to maybe write a user interface that actually accumulates this batch data as the front end, and this is your back end. But in general, this is how it runs in real life as batch predictions. Then there's just a very small Python trick I really like. How many knows about the LRU cache? No one? Cool. Okay. So a cache simply means it will look at a function and saying, hey, I am seeing you get n equals to 1. Let's say it gets, you feed this in with 1. Then it processes the function, and then it looks at what it returns, and then it stores those two. And next time you input 1, it says, hey, I already computed this. Of course, only use it if you have a deterministic function. I already computed for n equals to 1. So, hey, I now look up in my dictionary, which is a freaking fast operation, and I just return whatever Fibonacci is. And there's just some timings here. So this, without cache, it takes like 300 milliseconds, and this takes like microseconds. I think if you do the math, it's like a 300 million speed up or so. So you can also do this for your fast API. So if you assume that the users are going to request the same thing over and over again, you can implement the cache. And for those, you can like immediately return the output. And the nice thing is you can set like the max size, how many, like in this big dictionary, it has like how much data do I want to store? Because of course I cannot cache everything. There's some. Oh, when sharding is there? You cannot. Okay, we take the questions after. I think this was actually my last slide. So yes, sometimes I think about this movie and like, could I please be on this earth? Because oh my God, the training is taking too long. Come on. Cool. Okay, so there was some Zoom questions. Okay, when sharding, is there a CPU-like thingy keeping track of the internal communication between the sharded GPU, and if so, doesn't that bottleneck the GPU? Yes, there is a there is some bookkeeping going on. And yes, it slows down, but of course, there's been very smart people that try to reduce this bookkeeping that needs to be done. Let's say that we have nodes with different number of GPUs. Can we ask PyTorch Lightning to get as much devices as it can from each node? I don't think so. There are some assumptions when you run things in parallel that kind of things needs to be equal. So for example, a good thing that often confuses people, let's say you have 2 devices, you have 90 data points. You want to split those, 90 is a bad number. Let's say you have 3 data points, 2 devices. You need to split over those 2 devices. What internally happens is you don't get 2 and 1 sent out, you get 2 and 2. And one of the data point is a replication of the other data points, because the devices need to have an equal workload, because else you run into what we call race conditions, which is like the 2 devices are essentially racing each other to the, I don't know, button or the end of the script. And if one gets there before, you can end up with like this saying, hey, I'm done. Why aren't you here? Oh, I crash. That's the stupid explanation, right? But essentially, internally, we always try to make sure that each process is trying to do the exact same workload for things to work out. And it's very important, especially when we do testing, because if you have your test, you have your benchmark data set you want to compare to other people, you run that in distributed mode. Now suddenly you begin to have replications of your test instances. This can really screw with like your test metrics, which is the numbers you want to compare to people. During training, it doesn't really matter if we replicate like a single or a few data points, because it just goes all into the whole huge random stuff that's going on in our training algorithm. It doesn't matter. For testing, never use distributed stuff. Cool. Okay, I'm still sharing. Cool. I have it open here. So today's exercises, if you want to do just one thing today, I think it's just looking at the data loading. You can do this locally on your own machine. And it's essentially just a small exercise investigating the data loader in PyTorch. Because if you ever wondered what the fuck is the number of worker argument doing, this exercise can maybe help figure that out. Then there is distributed training. And the ugly truth is, this was the very first module I created for this course 3 years ago. And but the problem is it requires multiple GPUs to run, right? Which, let's be fair, nobody has that. Okay, if you have gotten multiple GPUs on GCP, nice, then you can try it out there. If you're a DTU student, you can run on the HPC. If you're a EOTech student, you probably have some university hardware. Like, leave this as a very extra exercise at some point when you're drunk or something. Yeah. And then there's like just a mixed bag of things you can also look into when trying to scale inference. So there is something about choosing the right architecture. So not all architectures are equal. Like some architectures are simply more efficient than others. So maybe this is worth looking into. There's also an exercise about quantization. So that's essentially when we try to replace our floating points with integer. What the heck happens, and can we still get good performance? The answer is yes. Pruning is I think it's, I haven't seen it used that much in production, but it's very much like a research-based thing. But essentially, when you have a large neural network, what you can do is a lot of the weights are very close to 0 often. So instead of actually propagating information through those weights that are very close to 0, maybe we can just prune them away, get a smaller neural network, and still have the same performance. Lower memory footprint, faster inference, yada, yada, yada. Maybe faster inference. And then there's like a small exercise in, or it's not small, it requires some implementation. Knowledge distillation is another technique that is commonly used if you want to get a smaller model. So let's assume you have a large model. It can do fantastic things, but you don't have room for that model on your whatever device you're running on or want to do inference on. So what you do is you train a small model to emulate or essentially predict the same output as the large model. And because the large model has kind of already figured out, like for a given input, how should I distribute the probability mass, it is much, you can get a much better, smaller model by training on that probability distribution of the large model than actually training on the labels of the input data. That's essentially what knowledge distribution is. But I can also see a lot of you have done a lot of stuff in this course. So if you just want to work on your project today, that's also completely fine. Okay. Thank you all. Okay. Last, brain is not working so well. Like I'm also working a lot on the side. If you don't like, so I acknowledge this course is very hard for you guys. You probably work like 9 hours a day. When I go home at 2, it's not because I stop working. Like I need to answer a lot of emails and make sure I actually have something to present and so on. So my brain is also rotten after 3 weeks. The next 2 days are project days. It's the same format as last week. You can come here. There will be some TAs. I won't be here tomorrow because I have contractors that come to my house that I need to look after. But I will be here on Thursday if you have like very final questions. Hopefully not at that point, but let's see. Okay. Cool. Okay. Done for me.